All right, so we looked at reaction rates, but reactions don't go in one step usually, so we need to look at reaction mechanisms. So these are the steps that sum up the balanced equation and agrees with the experimentally determined rate law. So here is a proposed mechanism. So those would be the steps, and there's the overall reaction, and the rate determining step. Notice it's second order in NO2, but the way NO2 was written each time, it's like it's first order in each of the reactants. That's why it was written like that. Okay. We're never going to prove a mechanism. We're only going to support it. It actually is going to remind you a lot of your research hypothesis. You can rule it out and you can support it. You can't prove it. Okay, so let's look at this. Okay, NO3 comes out of the first step and goes in to the second step. So that is an intermediate species. Okay. NO2 and CO go in only, so they are reactants. NO and CO2 are only products, so they come out. Look here, we had NO2 go in and NO2 go out, so it was here some excess. Sometimes something that goes in and goes out is a catalyst. So let's look at our example here. Okay. So we have C4H9Br. And so we've got to look for it. When we don't have it anywhere else, so it's going to be a reactant. Okay. C4H9 plus comes out and then goes back in. So that's one of those intermediate species that's made and then destroyed. We have bromine, doesn't show up anywhere else, so that has to be a product. We have H2O, only on the reactant side. So it's a reactant. We have C4H9O2 plus that is produced and then used again, so that's another intermediate. So that's all of our reactants. So C4H9OH, Br minus, and H3O plus. That is the overall balanced equation. The intermediates are the C4H9 plus and the C4H9OH2 plus, things that are produced and then used up. So the rate law expected would be from the slow step. So that would be rate equals K times C4H9 Br. Now, anything that's a reactant at the beginning and product at the end, we're looking at a probable catalyst.